The structure is the same as fixed size window problems. We slide a window of size k and update just one statistic, the current vowel count. We need the largest number of vowels found in any substring of length k. Given a string s and an integer k, return the maximum number of vowel letters in any substring of s with length k. Example 1 ends with answer 3. Substring Roman 3 contains 3 vowel letters. Example 2 ends with answer 2. Any substring of length 2 contains 2 vowels. The important sizing limits are 1 < s. Length < 105. S consists of lowercase English letters, and 1 k < s. Length. The main insight is that we do not need to recount all k characters every time. We only adjust the count for the character that enters and the one that leaves. When the window shifts right, add 1 if the new character is a vowel and subtract 1 if the outgoing character was a vowel. So in practice, the window size stays fixed at k, only the vowel count changes, and track the maximum count seen so far. The example highlights the reason sliding window is perfect here. The answer is just the best count over all windows of the same length. The best window is Roman 3, which contains 3 vowels, so the walkthrough goes in order. First, each slide changes the count by at most 1 up and 1 down, then the maximum count is the answer, and finally a fixed size vowel counter is enough. For the deeper version, the important thing is not more code first. It is naming the invariant that makes every local move safe. The long version should pause on the invariant or the local rule that makes the solution reliable, not just on the final code. So in practice, name the rule that stays true while scanning, connect that rule to the pointer or state movement, and then the implementation feels natural. Initialize the count for the first window, then update the count in constant time as the window slides. In the code, focus on 2 checkpoints. Watch where the answer updates inside the loop, then notice which value is returned to finish the reasoning. Here is the full solution. The entire algorithm is a constant time update to one window statistic. In the code, focus on 2 checkpoints. Watch where the answer updates inside the loop, then notice which value is returned to finish the reasoning. This stays linear time and constant space, and it is one of the nicest examples of fixed-size sliding window counting. Every character is processed once as it enters or leaves a window. So in practice, time complexity, O(n), extra space, O1, and this is fixed sliding window plus a frequency style counter. For more LeetCode practice, follow and subscribe to the channel. This is AI and human collaboration.